tell us about seriation.
Okay, thank you, Pablo. Thank you again for the invitation. So I think this talk is going to feel like a little bit like a tractability interlude. Okay, so things are a lot easier here than they should be, to the point of being almost supernatural. And so I'm going to talk about a highly classical problem related to rank aggregation. So some of the authors, the organizers have worked on this. It's very easy to describe. You have n items, and they could be anything you like, products, people, and so on. And you have a set of you have a little bit of information on comparison or preferences between these items. Okay, so you know that for a subset of the pairs ij, you know that item I is better than item j. Okay, and based on that, you want to find a global ranking of the items. Okay, so it's rank aggregation. You have very partial. It's a particular case of rank aggregation. You have pairwise information on ranking, and you want to aggregate this pairwise information to create a global ordering. Okay? That's it. Very ancient problem. It shows up in many, many fields. Of course, one of the most natural settings where this shows up is tournaments, sports tournaments. Okay? Typically, one team faces another, so you have a pairwise preference information or pairwise comparison that shows up. Your tournament is many, many of those pairs, and you want to produce a ranking out of the results. But in many other cases, the reason why pairwise information shows up is that when the question asked is a bit more abstract, it's sometimes much easier to reply in terms of relative preferences rather than produce an absolute score. So there are these websites similar to Hot or Not who try to rank people's hotness. And if I give you one picture, okay, giving an absolute ranking on hotness is difficult. But now if I give you a pair of pictures, ranking hotness is somehow a lot easier. Okay? The order is something subjective, so I'm not going to say anything. But this is also used heavily in marketing. For example, one of the two authors of a paper on pairwise ranking, Jamison and Novak, use it to rank beers. And the way it works is that you taste two beers, and you decide if you prefer one versus the other. You do that a couple of times. Of course, it has to stop. You have a limited beer budget in this case. And then their method will produce a ranking. Okay, and they have an app doing that, and so on. Okay, so it's in some cases that's the way the data is produced. In other cases, it's a much more intuitive way of producing ranking information. Okay, so it's an extremely old problem, and over the years, of course, a number of algorithms have been developed. And so I'm just going to quickly start by surveying the main categories of results on this ranking aggregation. So there's the cheapest thing you can think of, and if I give you 2 minutes to come up with an algorithm on this, is scoring. Okay, so you take the preference information for each item or each person or each beer and so on, and you produce a score based on the number of wins, essentially, and then you could just rank items according to the scores, right? So that's usually extremely cheap. Unfortunately, you get what you bargain for. It's usually not that robust, okay? There are more sophisticated versions of this scoring system. One classical, well-known system is the ELO rating system in chess. I'll give a bit more details about this. There's a TrueSkill. There's a ranking system produced by Microsoft for online gaming and so on. So you can refine this a lot, okay? And of course, the quality of the solution improves significantly as well. So that's the first type of solutions. You just produce a score, compare the score, okay? Second type of solution is a bit more subtle. They're based on the spectral argument, and this will be the main theme today. Okay, and I'll say a few more things about that, but clearly you work with a matrix, you capture a lot more information about your preference information, and in this case you pay a little bit a numerical price that's slightly higher, but you get a lot more robustness. Okay? Yes?
For spectral methods, this has been used in this context in general for sporting rankings since the 1930s. And
yes.
The analytic hierarchy process by Tom Saati was started by Tom Saati, is a huge area that's based on using the principal agent.
Yes. So I'm just surveying things that have been done before. This border dates back from the 18th century.
Yeah, but I think to give references from 2000 on for the spectral method, you should have given the references for...
Okay, so yes, one disclaimer, this slide should contain several orders of magnitude more references than, it's a massive field, so of course I'm omitting a lot of stuff, but I'm going to make references to this work in particular in what follows, hence the reason why I'm citing those. Of course, I'm forgetting a lot of people. And so spectral methods, I'll say a few more things about those later. The key idea here is that, well, it's also, you can see the matrix as a sort of way of capturing the preference, aggregating the preference information. There's work by the organizers, who I haven't cited either, on rank aggregation based on atomic norm arguments. There is classic work in statistics on maximum likelihood estimation method, on maximum likelihood based estimation, where you put a probabilistic model behind your observations on preferences, and then you try to infer your ranking information by maximizing likelihood. Okay, classic references include Bradley, Terry, Luce, in the 50s, but of course, many more people in this vein as well. And finally, in sort of increasing order of complexity, there are algorithms that use learning methods like support vector machines to learn a ranking based on a feature set generated from the preference information. Okay, so this is by increasing order of complexity. Scores are almost direct in some sense. Spectral methods take an eigenvalue computation, something of order n square. MLE requires maximizing likelihood. You solve an optimization problem. It can be a bit more expensive, even though there are fixed point-based algorithms to solve these things efficiently. And this requires solving something like a support vector machine. And so it's, again, a little bit more expensive. Okay? There is for everything that's missing in this slide, we have a solution. One of the co-authors here is producing a survey book on the topic that should be out soon. So, and that hopefully covers in a lot more depth the literature on the topic. Okay? So that's about algorithms. Of course, the problem itself has a different nature if you, in many of these references. So in many cases, for example, a partial subset of preferences is observed, not a full one. You can also be in a case where the preferences are fully observed but arbitrarily corrupted. There's a lot of work on actively measuring preferences, so choosing preferences so that you have you maximize your the quality of the reconstructed ranking using a limited budget of measurements. And in the statistical setting, so all these maximum likelihood estimation methods typically assume that you can make repeated observations. And of course, depending on the application you work with, repeated observations are possible or not. Okay? And obviously, performance metrics vary too in a significant way. A combinatorial way of measuring the quality of a solution is to measure the number of disagreements. Okay? And how does that work? Well, you have a reconstructed order. You simply count the number of arcs that point in the direction opposite to the order you've established. Okay? So these are inconsistent arcs. You count them, and that's going to be your performance metric. And yes?
Not clear on what you're assuming here. Is this ordinal or cardinal pairwise comparison?
It's what do you mean ordinal or cardinal?
Ordinal just means that you are saying I prefer this to this.
Yes.
You say by how much?
No, you don't say by how much.
But the spectral method you have to say by how much.
It depends. Some spectral methods, the one I'm going to discuss here, you don't say by how much. You just point. So, but I'll come to that. Just wait 2 slides and we'll be there. So that's it. So that's one way. You can try to minimize the feedback arc set. This is this set of arcs that point backwards compared to your reconstructed order. And there's actually a PTS for doing that. okay, on tournaments. So it turns out that on tournaments at least, this problem is easier than it should be because you can find a PTS. Of course, its complexity is even higher than the complexity I've discussed before. Well, in some cases, you're trying to maximize likelihood, so that's your objective. It's a completely different measure of performance. Convex loss in ranking SVMs. So it's a single problem, but there are many, many approaches, and it's sometimes hard to directly compare the performance of one method compared to another. Okay? So even comparing algorithms on comparisons is hard. Sorry. So just, again, a very quick survey of what's possible, just because it's interesting to see the wealth of methods that have been applied to this very single specific rank aggregation problem. The border count dates back to at least the 18th century. And in this case, it's very straightforward. The players are ranked according to the number of wins divided by the total number of comparisons. Okay? So if I give you 2 minutes to come up with a direct way of reconstructing an order based on pairwise preferences, this is probably something you would come up with. But there's a very long list of variants. I'm citing a few here. The ELO system is interesting, and I'm just going to detail it a little bit more here. And it looks a lot like the statistical methods that will follow. In the ELO system, players have a skill level, UI. It's their ELO score. Okay? And you assume that the probability of player I beating J is given by a certain function H, which is typically a Gaussian CDF, of the difference between the player skills. Okay? And so there is this total skill budget that's shared by all the players. And every time players play each other, they exchange skills. Okay? According to a formula. So when mu I wins, this variable wij is equal to 1, and the score mu I of the ith player is updated according to this rule, so it's the previous score plus a sort of dividend coming from the win, minus a penalty on how easy was this supposed to be. Okay? If it's an easy win, you don't update the score by much. If it's a huge win, you do.
So H is kind of the probability that a player with a skill I would win against a player with skill J?
Yeah, exactly. Yeah. And so that's used.
The probability was 1, you didn't learn anything from this experiment, so you don't gain anything?
Precisely. And it avoids the system being gamed, because then you otherwise you could choose very weak players, beat them, and increase your score massively. And of course, that's not the point. Okay? So that's the idea behind ELO. It dates back from the 70s. And the idea here is that if you look at the way the equation is updated, because H is a CDF, the total skill set of the group of chess players scored here doesn't change. So you just exchange skills, and that's it. Okay? It's like Bitcoin after the inflation ends. And there's a variation on this system where the skill sets of the players are represented by Gaussian distributions, and where you use statistical inference methods to basically do the same thing you're doing here. Okay? And again, the main point of these things here is that the numerical cost is very highly minimal. Okay? So you don't compute anything from a numerical point of view. So that's one obvious approach. Slightly different spectral methods. So the ones I'm going to mention today, and I'm sure there are others, but I'm going to focus on this one in this introduction, are similar to the classical ranking methods for the web. Okay? So on the web, you have this metaphor of a random surfer choosing pages at random, landing on a page, looking at links, choosing other pages, following a uniform distribution on the new page, and then you compute the global page ranking based on the stationary distribution. So the probability in the end, asymptotic probability of this random surfer being on a certain page. Okay? Here for ranking, it's the same thing. To every preference relationship corresponds a link. Okay? And the likelihood, so you still have this random surfer on the graph of preferences. And the likelihood of going from I to j depends on how often I lost to j. Okay? So you're going to visit people with more wins more frequently. Okay?
Since it's not reversible, how do you deal with this issue?
I don't know, actually. I don't remember. I'm not going to talk about this particular thing today. So, good question. I don't know. We should find out.
I want to point out that this is actually cardinal. It's not ordinal. Because you're not just going from I to j.
It depends if you repeat measurements or not. So in some statistical models, you're allowed to repeat measurements. And then, of course, the number of wins can be more than binary. If you have a tournament setting, then it's ordinal. Okay? So it depends on the setting. So again, this is just a very strict subset of what's out there. I just wanted to cover in 5 or 10 minutes as much as I could in terms of what's existing. Obviously, I'm missing something. Okay? Okay, so the good news about this is that, well, from an intuitive point of view, you're capturing a lot more information about the preferences and the structure of preferences in this matrix than you are doing in the scoring methods. Okay? Because this Markov chain captures all of the preference information you're given and stores it in a much more robust way. Okay? And from a numerical point of view, you're only paying a marginally higher computational price because, well, all you have to do is compute an eigenvalue, a leading eigenvalue of this matrix of dimension n, and the cost of doing that is proportional to n squared log n. Okay? So
Is it really that different from the previous
in the dense case.
Because you could think of it as some kind of power method or something like the previous thing, like the update of the scoring function.
Yes, from ELO starts to have this dynamical aspect. Hard to say, but at least here the dependence between the preference information and the final score is a lot more nonlinear, and you expect that to make it a little bit more robust. So this is a completely informal argument, but what I'm going to try to do at the end of this talk is make a more formal argument on robustness based on the structure of the matrix. So you hope that by storing your information in this matrix format, you gain in robustness, and you pay a slightly higher numerical cost. Okay? Any questions otherwise? Okay. So final, the last class of methods I'm going to cover today, maximum likelihood estimation. So here you have a model on where this pairwise information comes from. It's a statistical model. Comparisons are generated according to this generalized linear model. You have repeated observations, they're independent, and item I is preferred over item j with probability pij given by h of nu I minus nu j. Okay, so it looks very similar. It's similar in spirit to the ELO system. It predates it, so, well, the statement should be made in the opposite direction. Again, here nu is a vector of skills. H is a CDF, typically logistic in the Bradley-Terry-Luce model, but you can also do it with Gaussian or Laplace distributions. Okay? And so what you do now is just estimate nu by maximizing likelihood. Okay? And you can do that so you don't have to really do it using gradient methods. If you don't want to, there's a fixed point algorithm that typically works really fast. Okay? So that's the last major class of methods I'm going to cover. And so I'm going to just zoom on some of these methods and focus on the low complexity end of these results. Okay? And so the current trade-offs in that area, well, scoring methods are exact in the noiseless case. It's easy enough to figure out. They are usually designed for that purpose, but they're not very robust. Okay?
Alex, sorry,
yes.
one question. So here you assume that there is an ordering which is consistent with all the...
You don't have to in
But that's what you mean by noiseless?
Oh yes, that's what I mean by noiseless. So I haven't made any assumptions yet, but that's what I call noiseless. Yes, clearly. Yes.
I'm not sure what you mean by exact. You can have a scoring method where everybody prefers number 1 to number 3, but when you take a scoring method, it will give you number 3 higher than number 1. I can give you an example by text.
No, sure.
So what do you mean exact? I'm not sure.
Well, the board account with noiseless information on the full preference matrix will recover the exact ranking. So suppose you rank variables 1, 2, 3, 4, 5, 6, 7, 9, 10, blah, blah, blah. You get preference information based on that linear ordering. You compute the board accounts related to that ordering, and you reconstruct the ordering based on the scores. You get, you recover the exact ordering. That's all I mean by exact reconstruction.
Okay, I don't know what it means.
You take preference information consistent with a total ordering. You apply the border score to it. Yes, you get a. Yes.
So there are examples where you can give scores, and of course it's.
No. This is a general statement that applies to the most classical scores, border count in particular. That says that, well, the border count in the noiseless case will reconstruct the total ordering. That's it.
You're saying you assume that you just get all n-squared comparisons?
Exactly. They are all exact.
So in some sense, the number of wins tells you exactly your place?
Yeah. That's all I'm saying. That's all I'm saying.
Talking about partial preference.
No. In a few slides before, I was saying that in some of the papers I'm citing, the information is partial. In some of the papers I'm citing, there is active choice of preference information, so you can choose the preferences. These few slides are not results. I'm just trying to survey as fast as possible a very, very broad literature.
They're not clear, and they're important.
Okay. My apologies then. Anyway, so scoring methods are exact in the noiseless case, at least for most of them by design, but they are not very robust. Spectral methods are more robust for reasons I'm going to discuss later, but at least the ones that are cited here, that are based on this Markov chain argument, don't come with exact recovery guarantee, meaning that if you have full information, noiseless, you don't have any guarantee to reconstruct the exact ordering. Okay? And so, on the other hand, at the other end of the complexity scale, learning to rank methods are very expensive. And so we're not going to discuss these today. So the idea is simply today to connect the pairwise preference problem to another problem that also talks about ordering, but based on a completely different information set, which is ranking based on similarity or seriation. Okay? So I'm just going to make the connection between this pairwise, this ordering from pairwise preferences problem to another problem looking at similarity matrices, looking at similarity between variables and trying to recover an ordering based on these similarities. Okay? Yes?
So which category of the ELO thing fall into? Does that fall into the scoring methods category, or?
Which one? This one?
No, so the ELO yellow one?
Oh, ELO is at least in the references I'm citing here is in the scoring category.
Is it obvious that that one's not robust, or?
No, it's not. Very broad statements again. And robust to what also? So there are many things you can do to this information to torture it. You have typically missing values, you can have corruption, you can have adversarial, so the list goes on and on and on. And so very broad statements. But I'm going to talk about robustness in more precise terms towards the end of the talk.
So
Yes?
I'm asking, what's the property of that one that we're trying to improve? Like, what's the property that the ELO one has?
Oh, typically, so some of these scores, you switch one value somewhere. Suppose you have the full information matrix. I'll have a few slides that say this later on, but I might as well say it now. You start with the full information matrix. All preferences are fixed. They're consistent with the total order, and you switch one. And that's going to be enough.
If you accidentally won a grandmaster, you suddenly will become like a...
Whatever your fantasy is. And so you switch one, you create ambiguity in some of these core methods. And typically you don't, and again, typically should be qualified, but you typically don't in the spectral methods. That's what I wanted to say. Yes?
Where do algorithms for minimum feedback are set, for example?
Oh, so you remember that slide with methods ranked according to increasing complexity? I think that would be somewhere here. Okay? But on the other hand, it's a PTS. So, and again, their metric of performance is slightly different and so on. So that's it. That was just an introduction. Second introduction, seriation. I talked about it here last year, but I had 2 slides to sort of refresh your memory, 3 actually. So seriation is pretty easy to describe as well. Okay, it's a very natural problem. You have pairwise similarity information Aij on n variables. Okay, so you know Aij measures how close variables I and j are. That's it.
Symmetric or not?
Yes, yeah, this one completely symmetric. And so, and we're going to make one key assumption, and this is really important, which is that the data has a serial structure. Okay, so you're essentially measuring similarity on objects sitting in a one-dimensional manifold. So you unfold it, and then the geometry works right. Okay, and you can formalize that in numbers. So
the function mapping between the two is arbitrary. I mean, as long as it's decreasing.
For now, yes. Yeah. And so all you want is this R matrix property that says that there is a permutation of your matrix. So that characterizes this serial structure. There's a permutation of your matrix where the coefficients are decreasing as you move away from the diagonal.
Do you mean pi I minus pi j?
Sorry?
The definition of R matrix, do you want to say that the entries decrease with pi I minus pi j?
No. So you want it's given. You're not given the variable, the matrix. Sorry, in an ordered way. Sure. So there has to be for this condition to hold, there has to be a permutation of your matrix such that the coefficients move away from the diagonal.
Right, but the coefficients move away after permutation, right?
Yes, could be. Yes. Sorry. Then yeah.
So are you assuming that there are only 10 distinct values in this matrix?
No, this one is tuplets by accident. So I could generate a much more sophisticated example with bumps and so on. It doesn't matter. All you want is the decrease away from the diagonal. So there should be, it's easier to spell out graphically. There should be one permutation of the matrix, at least, that puts it in this 10th format.
What does it mean exactly? I mean, if it's not tuplets, then what do you mean by away from?
You just, then away becomes so it has to be decreased column-wise and row-wise. Yeah. Yes.
So as a follow-up to that question, is I minus j pi of I minus pi of j?
Yes. Yeah. So forget about the permutation thing. So the matrix, when properly ordered, should look like this. Okay. Except this one is a bit too simple because it's tuplets, but something like that. So it should decrease as you move away from the diagonal along lines and columns. Okay? And that's natural. You have a chain, so your variables are organized around a chain. You move away from one variable along that chain, and if things are properly unfolded, then clearly the similarity should decrease. Okay? Okay, so that's the R matrix assumption. And that defines this serial structure I was mentioning. Okay, so typically seriation problem is easy to spell out. Your input is not this; it looks like this, right? And you have a permutation. You have to find a permutation of your matrix that reconstructs it in this way, recovers the exact ordering. Okay, so that's a combinatorial problem written over permutations and so on. It should be hard, but it turns out that this is one of the rare examples where you have exact reconstruction results for spectral clustering. Okay, so you can solve this problem explicitly, provided that this assumption holds in a slightly stricter version, so you need strict inequalities in a few places and so on, but roughly speaking, this is the idea. Provided your data has this serial structure, then applying spectral clustering to the similarity matrix, which means forming the Laplacian and computing its second smallest eigenvector, the Fiedler vector, and recovering an ordering from the ordering of the coefficients of this eigenvector, that will provide you with the permutation you're looking for, the one that reorders the matrix in R format. Yes?
What's pre-R? Pre-R is
a permutation of, there are slides missing here. This is a permutation of an R matrix, okay? So you apply spectral clustering to the Laplacian of the disordered matrix, you recover the eigenvector, you sort its coefficients that gives you a permutation. That permutation will reorder the matrix. Okay? It's magical. And again, the computational cost of this is minimal. It's just n squared log n. Okay? So it's used, there are many applications of this thing, but one completely explicit is gene sequencing. It's not used actually right now in gene sequencing, but it's a good illustration of a problem that looks very close to that. Typically, we cannot read genomes, long strands of genome. So what people do is that they clone the genes, cut them into small pieces that can be sequenced explicitly, and then reassemble the pieces by looking at the similarity between the edges of those genome pieces, and then average the result once reordered, and construct a consensus sequence. Okay? So the similarity information for these small pieces of genes, they're called reads, are typically things that look very much like overlap. Okay, you look at the overlap between the edges of these reads, and that gives you a measure of similarity. Typically, reads coming from completely different parts of the genome will not overlap, so you get a similarity of 0. And then when there is significant overlap, the similarity increases. That's all you need. And genes have naturally this serial structure. Okay? So that's seriation. And so the idea today is to make the connection between reconstructing rankings from pairwise preference information and seriation. Both are ordering problems, or ranking problems if you want, and where is the connection? And it turns out that the answer is extremely simple, and also you can say a lot about the stability of the solution, much more so than in other spectral solutions. Yes?
You are implying that the matrix is full, all the entries are available, right?
Yes, but then I'll start from the solution where the matrix is full, and then study what happens when you start to remove entries or corrupt them. That's what I mean by robustness or stability. And it turns out that in some cases you can remove a lot of entries. So the matrix is not so full anymore, but it depends exactly what kind of regimes and error bounds you're looking for. Okay? So how do we go from this pairwise ranking from pairwise preference information to seriation? Well, the answer is deceptively simple. So suppose you store all your pairwise comparisons in this matrix C. Okay, it's +1 if I is ranked higher than Cij is +1 if I is ranked higher than J. 0 if the comparison is missing or there's a draw. -1 if J is ranked higher than I, and so on. And you're going to define a pairwise similarity matrix S match as essentially this quantity here. And what does this do? Well, it simply counts the number of matching comparisons between I and J with all other reference items K. And the intuition is very simple. You're in a tournament setting. And the idea here is to say that players that beat the same players and are beaten by the same players should have similar rankings. Okay? So that's all you're encoding here. You have your tournament result information here, and you're computing a similarity matrix between players based on two players will be close in the rankings if they are defeated and beat the same players. Okay? That's what you're measuring here. And in the case where you have full information consistent with the total order, everything is ordered, etc., S-match has a very simple format. It's simply n minus the difference between I and J. Okay? And that's a strict R matrix. So when properly ordered, the similarity matrix computed from the comparisons satisfies this serial R matrix condition, which makes spectral clustering work. Okay? In other words, that's one way of deriving a very simple spectral method for ranking from pairwise preferences. You take the preferences, construct a similarity matrix, and reorder the similarity matrix using spectral clustering. That's it. Okay? And of course, that's one way to do it. All you need to be able to do is to construct a similarity matrix that satisfies this R matrix assumption. So whatever your flavor of preference is, as long as it satisfies this R matrix condition, it will work. In particular, what you can do is try to increase the contrast, for example, by adding powers here. So there's an infinite number of variations on this methodology. It's just a new way of generating ranking algorithms, spectral ranking algorithms. Okay?
For the recovery to work, I guess it's not just enough that you decrease away from the diagonal. You need to decrease at some rate away from the diagonal.
There's no rate, but you need strict inequalities in a few places. So the sort of easiest way to prove this result is with a condition that states that the feeder vector should be strictly monotonic. And if that's true, then and the result is based on the Perron-Frobenius argument. I haven't had time to mention it, but typically monotonic vector is a vector whose increments are always positive, and so the proof works along the lines of the Perron-Frobenius result. That's where it's coming from. It's a paper by Atkins and others in '98, so there's a reference in the talk if you're interested. But there are no conditions on rates or anything. There are a few technical conditions on monotonicity and to make sure that things are unique and you don't have degeneracy, but that's it. Okay? So once you have that strict R matrix assumption, you know that spectral clustering will recover the true order. So that's one way to do it. But you can also do it if you wanted a generalized linear model. How does it work in 2 lines? Very easy. You have these probabilities, you measure them empirically, and you form you estimate a matrix SGLM, which is again 1 minus the difference of the observed probabilities of winning. Okay, and if you have enough samples, at one point this matrix is going to become an R matrix, and so applying spectral clustering to it will recover the true ranking. Okay, and so just to summarize these results very quickly. Again, if the items are ordered by decreasing values of the skill parameters, the similarity matrix SGLM is a strict R matrix, which means that spectral clustering will recover the true ranking. Same thing. Okay, so now robustness. I have a few more seconds to tell you about why inherently, or at least trying to convince you that spectral methods are inherently robust, at least these ones. And the reason for that is that those matrices are so simple that you can say pretty much everything you need about their spectrum. And if you know everything you need about the spectrum, you know everything you need about robustness, because then you can use perturbation arguments completely explicitly. Okay? So there are first a few things you can say just using counting and combinatorial methods. So, for example, robustness to corrupted entries. If you're given all comparisons between items order 1n, they're all consistent except one that you switch, and the gap between these two is larger than 2. Then the matrix will remain a strict R matrix, which means that, again, spectral clustering will recover the correct order. Okay, so there's a graphical way of seeing why this works. This is the comparison matrix well ordered with the full information set, consistent with the total ordering. The similarity constructed from this exact full information matrix. This is the similarity after 1 entry is corrupted, the comparison between 3 and 8. And you see that, you see, it's not immediately obvious, but what makes things work here is that the strict R assumption is still satisfied. Okay? And that would not be the case, for example, for a border count method. Okay? So you can actually generalize this argument a little bit more, further. Again, this is a kind of completely direct combinatorial algorithm, and show that actually square root of n corruptions will work with high probability if you pick them, if you locate them at random. Okay? You know that you need at least n square comparisons for exact recovery. So clearly you won't be able to go up to n square, but it's not clear exactly where this stops. So it might be possible to do more. We can't do that yet, but I'll switch to another argument later. And as far as I know, there's no exact recovery result of this type for the Markov chain type spectral methods. Okay, so what's interesting here is that the matrix you form to reconstruct the true ordering is extremely simple. Okay, this is just -1 + 1. Okay, and the similarity.
N squared, you mean if it's arbitrary, like for adversarial choice of the n squared comparison? Because generally you would think for exact recovery.
If they're picked uniformly, if
n log n,
if they're picked uniformly at random.
Then n log n should be enough, right?
No. So here you need n square. for exact recovery, but it's for exact.
For exact recovery, if there is a global ordering,
Yes.
and I tell you, and I give you n log n comparisons, wouldn't that be enough to?
I don't think so. No.
The argument's really silly. It's almost like somehow that
It's a bit counting.
always that I could flip something.
Yeah. It's.
Yeah.
I have to be robust, like.
Well, I mean, you have to get it the exact.
Yeah, it's exact here. There are softer versions of this result where things are completely different and where you get to n log n. So if you allow sort of a local, you want to constrain how much error you're going to make, then you get results at the rate n log n. So if you just care about not being too far, then n log n is okay, and it's actually optimal, clearly. But if you care about being exact, then n log n doesn't work anymore. Okay. So here, the sort of good news about this method compared, for example, to other spectral methods where you have this Markov chain matrix is that the matrix whose spectrum you're computing is extremely simple. It's tuplates, linear decrease, and so on. And so you know pretty much everything you need to know about its spectrum. And it's much easier to analyze than other Markov chain-based methods. Okay, so in particular, we can compute its Fiedler vector asymptotically. And same thing for the normalized. There are two versions, so I'm not going to go into details, but there are two versions of spectral clustering, normalized and non-normalized. The normalized, the non-symmetric normalized Laplacian is even simpler to analyze because it's a Fiedler vector is of this form, xi equals to a constant times I. So it's uniformly increasing. And in addition to that, so not only can you compute the Fiedler vector explicitly in this case, at least asymptotically, you can also control the spectral gap very precisely. And the spectral gap is what defines robustness for these matrices. Okay? So if you can bound the gap between the first, the second, and the third eigenvalue, you know exactly how robust your method is going to be to small perturbations, missing values, and corrupted entries. And here it's the case because you know exactly how to analyze the spectrum. You know pretty much everything you need to know about the spectrum of these matrices. So this is just a direct application of results by von Luxburg and others on the consistency of spectral clustering. This is a spectral clustering algorithm, so it's not a surprise. Asymptotically, S-match normalized converges to this linear operator. The degree function has this explicit format. You know, based on these results, that the range of the degree, the range of the degree is between 0.5 and 0.75. And you know from this paper then the bulk of the spectrum has to be contained in this interval. So the bulk of the spectrum is in this interval. You can also show that the second eigenvalue is outside of this interval. You can control the gap. And so you can control the stability of the perturbation argument in this case. Okay? And so this control on the spectral gap means you can use perturbation analysis to study the robustness of recovery completely explicitly. Typically, getting the second eigenvector or getting information on the spectral gap is the hard part in showing robustness. The key difference here is that the matrices are so simple that you get everything explicitly. Okay? And so this is the classical result showing by how much the ordering will be corrupted based on how much error you're making on the Laplacian because of missing or corrupted comparisons. This is the impact of the spectral gap. Okay, you have an explicit formula for the perturbation, but it depends on the rest of the spectrum, and you don't necessarily compute that. But typically, if the L infinity norm of the difference in these two vectors is smaller than the initial gap between your Fiedler vector coefficients, you're still going to have exact recovery because you're not going to be switching any coefficients. And so that means that if the error in the Laplacian is small enough, whatever this error is, you get exact recovery. So this simple perturbation analysis shows you that there's a region around the true matrix where you get exact recovery. Okay, and so very briefly, we're not done yet with those results, so it's a bit sort of a high-level discussion, but the way you corrupt the matrix is also highly classical, because you essentially corrupt the preference information matrix by subsampling it, so you have zeros appearing in the preference matrix, and we know exactly what the impact of subsampling is on the spectrum, because it's actually a method used in randomized linear algebra to speed up the computation of SVDs. You zero out certain coefficients, and that speeds up the matrix vector products you're doing in eigenvalue computations. Okay? And so there are results, for example, in Ashlob-Tess and McSherry, showing how to bound the error in the Laplacian matrix in this case, based on the number of entries you're keeping. Okay? So unfortunately, the perturbation argument does not allow us yet to improve the rate, the square root of n result on the number of allowed perturbation that we got previously, but at least all the ingredients are there, so hopefully we'll get something a bit more precise soon. Okay, so I have 0 minutes, but I'll take 2. So this is just a graph illustrating the difference at dimension 100 between the asymptotic formula and the true one for the Fiedler vector. So the point of this graph is that there is no difference. And so very quickly, I'll illustrate a few numerical results. So we essentially have a new algorithm, a new class of methods for producing ranking algorithms out of pairwise preference information.
These are for our matrices, right?
I'm sorry?
These are for our matrices, those matrices that we define.
So here we take a pairwise preference, a tournament matrix constructed from a total ordering, and we arbitrarily uniformly corrupt it or suppress entries.
But the matrix does not have, before you corrupt it, it doesn't have to be an R matrix.
Oh, no, it's just a preference information matrix. But if you square it and it's exact, then it's going to be an R matrix.
The entries are 0, 1, or -1?
Yes. But they're all +1, -1 if you're looking at the full matrix initially. Okay? And so there's no clear winners. So the long story short, there's no clear winning method. So I guess by design, the method I presented here in some of these experiments at least does better than the others. This is Bradley-Terry-Lewis. This is rank centrality, the other spectral method. This is the scoring. And in red is the seriation-based result. So it does better when you're near the exact noiseless regime, okay, in these experiments. But it's not always the case. Sometimes you have this nonlinear behavior that we don't understand. Clearly, it behaves completely differently. That's at least all you can say. So here, this was higher is better. We knew the ground truth. Here we don't. We just minimize the number. We just study the number of upsets. This is on a top coder coding competition. And again, you see that, well, at least on both these examples, this spectral solution, so the seriation-based solution, does better than the rank centrality spectral solution. It does, of course, all these algorithms do better than the point score. And they both Bradley-Terry-Lewis and the seriation-based algorithm do better than the system used by the top coder website. Okay, you can do supervised ranking recovery, but I'm not going to talk about that. And of course, none of these results are stable. So this is a top coder over the years. So this is 1 year where things were very noisy, not that noisy, and these are 2 years where it's not clear at all what's going on. Okay, but at least the behavior is completely different. So there's some innovation. This was presented in Britain, so they wanted to know about football. And so just to finish, I'm recruiting a little bit of advertising. I'm recruiting postdocs for 1 or 2 years at École Normale Supérieure. This is more or less the view from our office. And, and so if you're interested, send me an email at this address. And so just to conclude, thank you for giving me a few more minutes. We have a new way of generating ranking algorithms, spectral ranking algorithms based on seriation results and essentially what is an exact recovery result for spectral clustering. And the nice thing about this result here is that there is an almost completely explicit perturbation analysis. And it's not that frequent that you can go as far in the details in the way you analyze perturbations. Here, everything is computable, which is really nice. And it seems to be more robust in certain settings. And coming soon, so we have talked a lot about what happens near the regime where you have full information, it's noiseless, and so on. And we need to say a bit more about the other end, the one you were talking about, where you're close to n log n at the completely other end of the information spectrum, and we don't have good stability results there. So that's to do. The paper will be at NIPS in December, and there's a subset of these results on arXiv. Thank you.
comments, Alex?
I guess this is probably something that you covered in your talk already, but so there is this model of Braverman and Mossel where they flip the comparisons with probability epsilon, right? Some half minus epsilon.
Okay.
And they give an algorithm to recover the ranking, dynamic programming based algorithm to recover the ranking.